Hello and welcome to the third and final part of Chapter 8. Today we're going to look at sections 8.6, 7, and 8. When looking at section 8.6, we're going to talk about what we call resonance structures. Now sometimes when we look at molecules or ions, experimentally, we find that the actual arrangement of atoms aren't really adequately described by a single Lewis structure. Meaning that sometimes there's different structures that could be drawn and there would possibly be a better one that we should be looking at. And a prime example of this is ozone. Ozone is O3. And if we were to go and calculate or draw ozone, you may come up with a sketch that looks something like this. It has all of the valence electrons accounted for. We see that we have a partial positive here and a partial negative here. So everything seems legit. However, what we found is with ozone, both O bonds are actually the same length, and both outer oxygens have a charge of a -1/2 instead of your typical -1. So what we can conclude is that one Lewis structure may not actually be able to accurately represent what the molecule looks like. And if you notice, right here, we have two molecules that look very similar, with the exception that I have a double bond here and a single here, and on this molecule I have a single bond and a double bond. Now, because these are both the same thing, essentially, these are what we call resonance structures. And we use the multiple structures or resonance structures to describe our molecule. And maybe to get kind of a better understanding of why we need resonance structures is if you think about when you're mixing colors, if you mix the colors in equal quantities of blue and yellow, we know that we're going to produce the color green. However, if we go to describe green in terms of its single primary colors, we can't really do that because green has its own identity. And what I mean by its own identity is it doesn't show characteristics of blue and it doesn't show characteristics of yellow. It's not either one of those colors part, or some of the time it's always green. Likewise, when we're looking at resonance structures, we can't really say, well, our structure is always going to look like this or it's always going to look like that. We say that it's going to create ozone, which is going to be its own unique molecule. So when we think of resonance structures, we think of this as being a synthesis of the two structures itself, or kind of a combination of both structures. Likewise, if we look at a molecule like CHO2-, we'll see that the electrons that form the second carbon and oxygen bond in the double bonds below don't always sit right between the carbon and the oxygen, but sometimes they can actually move between the two oxygens and the carbon. Now, when we say that something is moving, they are not localized, but they are delocalized. So in other words, if you see something that's delocalized, we know that there's going to be a little bit of freedom for movement within the electrons. And a prime example of this is going to be in the resonance structures of what we call benzene. And benzene is an organic compound, and if you ever go on to take organic chemistry, you'll study benzene quite a bit, but it's represented by C6H6, and it has two resonance structures. And you can see those two resonance structures right here. And what you'll notice is we have double bonds going every other carbon, and they're either going to be like at your top, lower right, lower left, or they're going to be upper left, upper right, and bottom. So it's commonly represented as a hexagon, which you can kind of see we've got that going right here, with a circle inside. And you can see this right here. Now, there's really no need to put on the hydrogens because when we're in organic chemistry, when we deal with benzene and that kind of stuff, we assume that at each one of these points, a hydrogen is actually veering off from that. Now, the circle inside, what that does is that kind of represents the delocalized or the free-moving electrons within that benzene ring. All right, now we're going to look at section 8.7. 8.7 deals with the exceptions to the Octet rule. If you remember back in section 8.2, I told you that the Octet rule was a general rule of thumb, however, there were exceptions. Well, this is a chapter where we're going to hit this is a section where we hit those exceptions. And to start out with, and if you want a more detailed explanation or want to read more about this, 8.7 actually starts out on page 322. So, when we look at our exceptions, there's going to be 3 types of ions or molecules that do not follow our octet rule. The first one is going to be when we have ions or molecules that have an odd number of electrons. Then we're going to look at ions or molecules that have less than an octet. And thirdly, we're going to look at ions or molecules that have more than 8 valence electrons. And when that occurs, we're actually going to have to expand our octet. So to start out with, let's look at the odd number of electrons. Odd number of electrons are pretty rare. And when we get an odd number of electrons, we actually have an unstable and a highly reactive molecule. And an example of an odd number of electrons is something like what you see here. If you notice, we have nitrogen and oxygen. Nitrogen has 1, 2, 3, 5, 7 electrons. Oxygen has 2, 4, 6, 8. So we notice that we have 7 electrons here, and we do have 8 here. Now we can also look at it where nitrogen then would have 2, 4, 6, 8, and oxygen would only have 7 because we have 2, 4, 6, and 7. And just to list off a few examples where we have an odd number of valence electrons would be something like ClO2, NO, NO2, and oxide, which is O2 minus. And because of that, the complete pairing of electrons is virtually impossible, and that's why this has to be an exception. Next, we're going to look at the case where we have fewer than 8 electrons. Again, this is a situation that is relatively rare, with the exception of hydrogen and helium, of course. And although this is rare, this occurrence is typically going to happen when we are dealing with boron and beryllium. So let's just look at an example, and right now we have boron trifluoride. And if you follow like the first 4 steps when we're drawing Lewis structures, you're actually going to get a structure that looks something like this here, where we have fluorine, boron, fluorine, and fluorine. And fluorine is going to have lone pairs of electrons all around. And what you'll see is fluorine is completely satisfied. However, boron has only got 2, 4, 6 electrons. Now, if we go ahead and create a double bond, which is what you'll see in these cases here, what we do then is we actually have 3 equivalent resonance structures. Okay, all I've done is shifted that double bond around. And by doing so, what we're doing is we're actually forcing fluorine to share electrons with boron, which is actually inconsistent with our high electronegativity of fluorine, because that doesn't usually happen. And when you look at the formal charges, you'll even notice that boron is the one that ends up with a negative charge on it. And if you recall, that shouldn't occur because boron is less electronegative than fluorine is. Now for drawing sakes, if you do end up having to draw it, although these are resonant structures, this right here is typically how we would draw a Lewis structure for boron trifluoride. And that's just reiterated right here in this slide. So if we want to make a conclusion out of this, we can actually conclude that if we're filling the octet of a central atom and it results in a negative charge on that central atom, in this case here where boron was getting a negative charge on it, and we're getting a positive charge on the more electronegative atoms, which in this case was fluorine, then we don't need to fill the octet of the central atom. That's why boron then is essentially only going to end up with 6 electrons. In our third variance to the octet rule deals with the case of when we have more than 8 electrons. This is actually the largest class of exceptions. For example, if you look at the molecule phosphorus pentachloride, you'll see that we have to expand the octet of atoms. Okay, and that's because phosphorus can only exist if there's 10 electrons around it. Now, this usually happens when we are in the third row of the periodic table or below, and that's presumably because of the d orbitals that are participating in the bonding. At times, you may see some Lewis structures written with an expanded valence shell, even though the structures can be written with an octet. For example, if we look at the Lewis structure for the phosphate ion PO4 3-, you'll see that both of these will actually fulfill our octet rule, and they fulfill the electron count as far as coming up with a charge of a -3. However, the better structure will put a double bond between the phosphorus and one of the oxygens. Now, keep note, it doesn't matter which one of these oxygens are taking on that double bond. This right here is just one example of a resonance structure. By putting that double bond in, what happens is we are eliminating the charge on the phosphorus and one of the oxygens, which just so happens to be this one right here. So, to kind of sum it up, if the central atom is coming from the third row or below, we want to expand its octet to eliminate some formal charges if we can do that. And if we can, then that's going to be our preferred method. So example 6 then says to draw the Lewis structure for ICl4-. So the first thing we're going to do is we're going to do our valence electron count. We have 7 valence electrons in iodine, and then we have 7 valence electrons in chlorine, and I have 4 of those. Oops, multiply that by 7. We're going to add these together, and then I have to add one more electron because of my negative charge right here, because this is really ICl4 with a minus. So I'm going to add one more electron, and this is going to give me 4 times 7 is 28, plus 7 is 35, plus 1 is 36 valence electrons. Our iodine atom is going to be our central atom, and we're going to have chlorines coming off in each direction. By putting 4 electrons around all of the chlorines, that's going to give us 32 electrons. So I'm going to subtract my 32, and I still have 4 electrons remaining. So because iodine is actually larger, we're going to put those 4 electrons on iodine instead of chlorine. So I'm just going to kind of fit these in maybe right here and right here. So now I can subtract my 4 and get a total of 0. And what we'll see as we come into Chapter 9, the structure of this is actually going to look something like this. And then our iodine is going to have the 2 valence electrons like that. Or you could put them on top and bottom. The last thing we're going to talk about in Chapter 8 deals with the covalent bond strength. Now, the stability of a molecule is related to the strengths of the covalent bonds that it has. And the strength of a covalent bond between 2 atoms is actually determined by the amount of energy that is required to break that bond. So, this is what we call our bond enthalpy. And bond enthalpy, for instance, of a chlorine-chlorine atom, or chlorine-chlorine bond, you can see it's got a single bond in between. And just so you know, this is actually designated as D and then whatever your bond or your atoms that are being bonded together is. So this is measured to be 242 kilojoules per mole. And if you look on page, I'm going to write this right here, page 326 of your textbook, you will see this chart right here. And this chart contains several average bond enthalpies for several different types of bonds. Now, if you notice, your bond enthalpies tend to be positive because the bond breaking process is an endothermic process. In other words, it's going to absorb energy in order for that bond to break. And one thing I want you to take note of is that these average bond enthalpies are not average, or I'm sorry, they are average, they're not absolute bond enthalpies. Okay, and what I mean by that is, like, if you look at the CH bond in methane, this is actually going to be slightly different than the CH bond in chloroform. However, they're going to be treated the same because there's just an average. So it may take a little bit more or a little bit less, depending on the amount of energy, depending on the molecule that the bond is in. However, when we do calculations, it's all based on averages. Another way for us to estimate the change in enthalpy for a reaction is to compare the bond enthalpies of the bonds broken to those of the new bonds that are formed. And that's really what this diagram is showing you. If you break a bond right here and you make a new bond, the difference is going to be the change in enthalpy. So in other words, our change in enthalpy of the reaction is going to equal the summation of the bond enthalpies of the bonds that are broken, or the sum of the bonds that are broken. And this right here and this right here is actually supposed to be sigma for the summation. So the change in enthalpies of the reaction is going to equal the sum of the bond enthalpies of the broken bonds minus the sum of the bond enthalpies of the bonds that are formed. So in a nutshell, if we have something like CH4 plus Cl2, we're going to get CH3Cl plus HCl. And we have one CH bond and one Cl bond, and both of these are being broken to form new bonds, and the new bonds that are being formed are the CCl bond and an HCl bond. So in order to find the change in enthalpy of the reaction, we're going to look at these, and then take the difference between the two. And I wanted to leave this slide on. It looks kind of messy, but this here should actually be the delta H. So delta is the triangle. Okay, the notation is to take D of the CH bond plus D of the CCl bond, or the enthalpies of my bonds that are being formed, and we're going to subtract the enthalpies or the energy required to break the bonds of my original bonds. So that's what this D of the CCl and the D of the HCl are. Now these values here that are being plugged in are actually coming from that table on page 326, and you can look those up. So we're going to add those together, subtract them. This is what we get. This is our net difference. So let's give it a shot. For example 7, we're going to use the table from, or table 8.4, which is on page 326, and estimate the change in enthalpy for our following reaction. And we're given the little note that says that we want to explicitly show the bonds that are being involved in the reactants and the products. So for my bonds that are being broken, we are going to break 6 CH bonds. And I have 1, 2, 3, 4, 5, 6. None of these are going to be over here, so that's how I know 6 of them are being broken. So I can say that the change in enthalpy is going to be equal to 6 times D of my CH bonds plus, and I'm going to put this in brackets, it looks like my carbon-carbon bond is being broken, and I see that I have one of those, so I'm going to write in D of my carbon-carbon bond, and we're also going to be breaking 7 halves of our D of our O2 bond, or our OO bond, however you want to write it. So these are my bonds that are breaking, and from that I'm going to subtract the values of my bonds that are forming. So I'm just going to go minus the bonds that are breaking, or I'm sorry, the bonds that are forming are, I see over here between oxygen and carbon, so I'm going to say D of OC. I actually have 4 bonds that are being created, and I get my 4 because I have 1, 2, 3, 4. So I'm going to place a coefficient of 4 on there. Then I'm going to add that to my oxygen and hydrogen bonds. So I have D of my oxygen-hydrogen bonds. I have 2 oxygen and hydrogen bonds here, but I have 3 of them. So that's actually going to give me 6. And that's all I've got for bonds that are forming. Now, if I go and I plug in the values that are given, again, based on that table, I end up with 6 times 413 kilojoules plus 1 times 348 kilojoules plus 7 halves times 495 kilojoules. And I'm going to subtract from that 4 times 799 kilojoules plus 6 times 463. Oh, let me rewrite that down below. So 6 times 463. So when I go ahead and I add these up and subtract, we get a negative 1,416 kilojoules is the difference from my bonds breaking to my bonds that are being formed. Okay, and just like we are able to define an average bond enthalpy, we can also define an average bond length for some common bonds. Now this table here can actually be found on page 329. And what it does is it lists some average bond lengths. And the one thing I want you to take a note of too is when you look at the bond lengths between a single bond, a double bond, and a triple bond, you should look or notice that the length actually gets shorter. Now the shorter the bond is, the more that the enthalpy is going to increase. Also, the shorter the bond, the stronger the bond. So if you notice, our single bonds are longer than our triple bonds based on the numbers here, which tells us that our triple bond is going to be stronger than our single bond. And if you think about it, it makes sense. Kind of think about a rubber band. If you have, let's say, like 2 balls that are being bound with 1 rubber band, you can probably stretch that rubber band until it breaks. Well, if you go and you put 3 rubber bands on there, you're going to have to break 1 more bonds, and 2, typically when you put like more springs or more rubber bands on something, it's going to have a tighter pull, and it's going to require more energy to break those bonds. So if you have questions on this, please be sure to ask me tomorrow in class. Otherwise, I hope you guys have a great night, and we will see you tomorrow.